Good day everyone, my name is Ginanjar Suwasono, and I'm delighted to present our research paper titled Vision Algorithms on Identifying Vacant Parking Spots Using Vision-Based Approach. This study is the result of the collaborative effort between the Artificial Intelligence of Things Research Group at Politeknik Negeri Malang and the Computer Vision Laboratory at Politeknik Negeri Bandung. I'd like to acknowledge the significant contributions of my co-authors from Politeknik Negeri Bandung, Professor Hertog Nugroho, Mr. Griffani Megiyanto Rahmatullah, Mr. Muhammad Yusuf Fadhlan, and Mr. Dinan Mutamaddin. Now, to set the stage for our research, let's dive into the background of the study. The scarcity of parking spaces in highly populated cities is causing difficulties for people to park their vehicles, leading to issues like traffic congestion, inconvenience finding suitable parking spots, and limited accessibility. This also impacts their overall vehicle trip experience. Consequently, effective parking lot management necessitates real-time monitoring of vehicle parking occupancy. Being aware of available spots and providing this information to users can decrease bottlenecks, improve scalability, and quicker identification of vacant parking areas. Different approaches have been suggested to deal with the issue of parking management in urban areas. Solutions using wireless sensor networks are well regarded for their ease of implementation, affordability, and ability to work with different sensors that can monitor parked vehicles. Sensors such as ultrasonic, inductive loop sensors, and infrared are frequently employed in the WSN research for smart parking management systems. However, the enormous number of parking slots might create real-world deployment challenges, leading to high maintenance expenses. Additionally, each sensor is being assessed using thresholds to decide the occupancy state. Despite this simplicity, the sensor's limits in object identification and lack of intelligence degrade accuracy, leading to potential false detection. In recent years, various computer vision methods have been proposed to tackle challenges associated with parking lot management. These approaches focus on analyzing images captured from parking areas and address various goals, such as identifying the boundaries of each parking space, classifying individual parking spaces to determine if they are occupied or unoccupied, and counting the number of vehicles in images. Furthermore, the availability of public image datasets and rapid growth of deep learning technology have produced several state-of-the-art in vision-based parking management studies. Computer vision techniques have an edge over individual sensors in WSN-based systems. These methods can cover extensive parking areas using just one camera, avoiding the necessity of a separate sensor per spot. This minimizes setup and maintenance costs. Furthermore, camera can aid in tasks like surveillance and identifying unusual behavior. This study addresses the problem of recent occupancy detection methods in parking surveillance systems. Existing methods exhibit limitations including vague slot definitions, high computational costs, and potential bias issue. Moreover, certain classification approaches utilize patches for slot assessment, introducing problems related to overlapping annotations and limited feature information for distant slots. These limitations highlight the necessity for a more accurate and adaptable approach to occupancy detection in parking surveillance systems. The major contributions of this research include: first, the proposed system architecture distributes the computational load between slot initialization and the optimization of a deep learning framework aiming to enhance system performance. Second, a fusion detection method is introduced to accurately determine the occupancy state of parking slots, improving adaptability and resilience, particularly in scenarios with occluded vehicles. Third, three occupancy algorithms such Euclidean Distance, intersection over union, and intersection over reference are compared to evaluate the vacancy status of parking slots. Last but not least, this method significantly outperforms state-of-the-art techniques in accuracy, performance, and robustness. The proposed framework's overview is presented as a flow diagram in this picture. It consists of two main components. First, data processing and training, and second is data testing and occupancy detection. Assuming that each camera position is fixed to monitor to desired area in the parking lot, we begin by manually annotating and labeling each parking slot to obtain region of interest. Once all the desired slots have been annotated, the resulting coordinate vertices for these slots are saved as blobs in our system for future use. As part of the vehicle detection method, we utilize ULOV7 due to their optimal accuracy and efficiency for object detection tasks. To improve the robustness and accuracy of our system's performance, we propose a combination of object detection and occupancy state algorithms, which will be explained in the following subsection. Given an image of parking area, each parking slot is manually annotated to give a close approximation of its true form based on four coordinates as shown in figure below. Let's say k is equal to 1 to 4, where x sub k and y sub k represent the horizontal and vertical axis coordinates of each parking spot respectively. Then a unique ID is assigned to each parking space based on the ith row and jth column indices. We represent each parking space with its ID as a list of A. It should be emphasized that the value of J for the jth column may vary across different rows, which is indicated by M. As a result, a tuple may represent the complete specified slot ID along with its coordinate as expressed in here. On the top right image, you will see a raw image from camera 8 from our dataset, and the below image is a representation of slot initialization based on the same camera view. CNRPark-EXT dataset used in this research consists of 810 parking lot images gathered from 9 cameras with different viewpoints and various environmental conditions. This dataset contains information on the binary classifications of two labeled classes. However, since we want to increase the robustness and accuracy in our system instead of using binary classification, we used instance segmentation, and we did a resizing the input image into 640 by 640 pixels so that this input will be compatible with the ULOV7 detector. Additionally, we annotated vehicles individually as polygon shapes for segmentation purposes. Moreover, by rotating our train set randomly between 15 degree clockwise and counterclockwise, so that we gathered frames with a total of 16,653 car instances from the CNRPark extended dataset. Then we randomly divided all dataset from 1,243 images with the portion of 70%, 20%, and 10% for the train, validation, and test set respectively. After data preparation was completed, we processed the training set for transfer learning to achieve the best ULOV7 model. Finally, the best weights from the evaluation process were applied to our system for future use. In intersection of a union was implemented to estimate the state of each slot. The key of this algorithm is to compare the intersection of a specific slot denoted by ROI as sub ij and the area of a selected car denoted by ROIC sub n. Since the shape of every parking space might vary, taking on the form of a polygon, we can measure the region of interest of each parking space by using the quadrilateral equation as this. Hence, the IOU can be computed as the maximum of the intersection between the area of slot intersection with the area of the car divided by the union of the area of slot and the area of the car. The output of the slot state after performing the IOU algorithm can be expressed as the predict slot state, where it will be occupied where the IOU value is greater than the threshold value, and it will be vacant if it's otherwise, where the threshold value is the ratio of the union area of slots and the car. We propose the intersection of a reference algorithm to minimize the error of false detection in occupancy state detection. This algorithm aims to maximize the occupancy area of a detected car onto an individual slot by modifying the divisor of IOU as a factor of reference area, which is ROI S sub IJ. And then, to predict the slot state of this algorithm, where the threshold value can be set as the proportion of each individual slot area. Where the IOR value is greater than the threshold, it will be occupied, and it will be vacant when it is otherwise. Additionally, we also apply a sorting mechanism to prevent redundancy of a certain vehicle occupying more than one slot using argmax function for IOU and IOR algorithms in this study. To perform the Euclidean distance algorithm, the centroid of every individual slot will be assessed for all detected centroid car. From this formula, each element represents the coordinates of every distinctive slot. The first-order image moments are calculated to provide the centroid of each vehicle detected in the frame after running YOLO v7 inference. This requires adapting a grayscale image with pixel intensity represented as I, x, y, which allows for the computation of image moments m sub vw. These moments are used to calculate the centroid of the instance car in the direction of x and y. Thus, the centroid of all detected cars can be calculated as c sub n, x, y. After obtaining the centroid of the car and the centroid of the slot, we perform Euclidean distance for all centroid slots to every centroid of detected cars by the following equation, where P is the element of the centroid of the car, and the Q is the element of the centroid of each individual slot. Let's the threshold be the shortest diagonal for all individual slots of slot J in row I, where the components of vector threshold I sub j represent the value of thresholds for every slot J in row I. Thus, the predicted slot state will be occupied if the distance of the centroid car and the centroid of the slot is less than the threshold value. Note that to avoid redundancy of a particular slot occupied by more than one vehicle, we implemented a simple sorting procedure that will evaluate those specific slots only with the closest vehicles. These are the comparison between YOLO v7 performance with default hyperparameters and optimized hyperparameters during the training phase. Initially, we trained YOLO v7 with its default hyperparameters for 50 epochs using our dataset. The figures displayed here illustrate the training and validation loss as well as the overall model performance when using the default hyperparameters. From the graph on the left, we observe that the validation loss begins to saturate around the 17th epoch, while the training loss continues to decline slightly until the end of the training process. These patterns suggest the potential onset of overfitting, where the model may be learning the training data distribution too well, impairing its generalization capability. To address this, we proceeded to optimize the hyperparameters and refine the training process of YOLO v7. Our goal was to mitigate overfitting and enhance the model's ability to generalize beyond the training data. After testing various configurations, we identified the optimal hyperparameters for our data distribution. We extended the training to 500 epochs with early stopping set at 20 epochs patients, and we switched to the SGD optimizer with specific settings: an initial learning rate (LR0) of 0.001 and a final learning rate or LRF of 10 e⁻⁻⁶, the momentum set to 0.9, warm-up epoch set to 1.0, and mix-up set to 0.5. It's important to note that all other unspecified hyperparameters remain at their default values. This optimized setup significantly improved the model's performance by preventing overfitting and enhancing its generalization ability, and reflected in the subsequent performance metric. As a result, to the comparison of performance analysis for proposed methods using different metrics, generally, the Euclidean distance algorithm demonstrates an upward trend as its threshold value increases with respect to accuracy, recall, and F1 score metrics. In contrast, the IOU and the IOR algorithms exhibit higher scores for these metrics at lower threshold values, and their performance tends to decline as the threshold value increases. The sample results of occupancy detection from proposed methods using best threshold parameters are depicted in this figure. The regions in red area are indicated as occupied slots, while the green areas are specified as vacant slots, while the blue areas represent detected vehicles through instance segmentation using the YOLO V7. We have summarized the comparative analysis between our research and the state-of-the-art for occupancy detection in parking surveillance systems in this table. It is essential to highlight that there can be variation in terms of system inputs and computational process across different systems. Furthermore, we emphasize evaluating system performance and the primary algorithm procedures. It is important to note that the test procedure for few studies may have led to biased results, or it is not clear how they define the specified or observed slots. Generally, it shows that our approach endeavors to preserve the information of each slot to the greatest extent feasible by emulating designated slots akin to the real shape conditions. As evidenced by the system performance outcomes, the accuracy of the Euclidean distance algorithm within our proposed method slightly surpasses that of the state-of-the-art performance. In conclusion, the proposed fusion algorithms combine computer vision techniques with occupancy state algorithms, resulting in enhanced accuracy and robustness in system evaluation performance. The developed pipeline integrates object detection through an optimized YOLO V7 framework with multiple occupancy state algorithms, including IOU, IOR, and Euclidean distance. Moreover, comprehensive experimental evaluations provide valuable insights into the performance of these methods, demonstrating the approach superiority over state-of-the-art techniques. With the accuracy of 98.88% for the Euclidean distance algorithm, 90.05% for the IOU algorithm, and 97.99% for the IOR algorithm. This research advances the field by offering an innovative solution that surpasses existing methods and contributes to the development of more reliable parking surveillance systems. I hope this presentation has highlighted the potential impact of our work, and I encourage you to think about how such innovations can shape the future of autonomous systems. Thank you for watching and have a great day.